Hi, my name is Leo, and today we'll be looking at population genetics. For this study, we'll be looking at a species of mouse that live in a forest where the ground is mainly covered in dead leaves and dirt. These mice are all of the same species, with the only difference being their coat color. The black color corresponds to the big A genotype, the brown color corresponds to the big A genotype, and the white color corresponds to a genotype. We can assume that this population is under the Hardy-Weinberg equilibrium because there are no stressors currently on this population. To begin the study, we collect 100 of this species of mice, and the numbers we collect are as follows: 52 black mice, 15 brown mice, and 33 white mice. Using these numbers, we can calculate our genotype and allele frequencies. To calculate genotype frequency, we take the number observed and divide by the total, which in this case is 100. To calculate our allele frequency, we first take our heterozygote genotype frequency and divide it by 2, then add to the genotype frequency of big A and little a respectively. This number should equal 1 when added together, if we are under equilibrium. Another way to test this is by using the Hardy-Weinberg law. This law assumes that our population is infinitely large, randomly mates, and has no selection, migration, or mutation events. To use this equation, we plug in our allele frequencies for big A and little a as P and Q, respectively. Unfortunately for these mice, an owl has entered the ecosystem, and due to the coloration of the ground and the color of the brown mouse, the owl will most likely target the black and the white mice as they do not blend in as easily as the brown colored mouse does. This type of natural selection event is called stabilizing selection, in which the heterozygote genotype is favored. From this, we can calculate our new survival rate. The survival rate is the percentage of the phenotypes that survive to reproductive age. Using the survival rate, we can calculate our relative fitness by taking our survival rate number and dividing by the highest number, which in this case is 30. Next, we can get our survival number. We get this by taking our previous genotype frequency and multiplying by the relative fitness. Now that we have a survivor number and a total for that number, we can calculate a new genotype frequency after the natural selection event occurs, much like the same way we calculated the genotype frequency at the beginning of the study. We can again calculate a new allele frequency the same way by taking our heterozygote genotype frequency, dividing by 2, and then adding to the big A and little a genotype frequency respectively. As you can see, our big A genotype frequency has decreased from 0.52 to 0.40. Our big A little a genotype has increased from 0.15 to 0.35, and our little a genotype has decreased also from 0.33 to 0.25. The allele frequency for big A has decreased from 0.595 to 0.575, and our allele frequency for little a has increased from 0.405 to 0.425. If this natural selection event continues into the future, we can expect our heterozygote genotype frequency to increase, while our allele frequencies will get closer and closer to each other.